Welcome viewers, this is second lecture on linear algebra. In my first lecture we have given the definition of a real vector space. To review it, I'll first again give you the definition of a real vector space. A triplet V, a set and two operations plus and star forms a vector space provided certain axioms are satisfied. The first axiom is that the operation plus and star, we call it scalar multiplication, are closed in V. The addition is commutative and associative. Further, the existence of additive identity is there in the set V, and existence of additive inverse is also there in the set V. As far as the scalar multiplication star is concerned, it satisfies distributive properties with respect to vector addition, and star is also associative, and there exists a scalar 1. If all these properties are satisfied, then V plus star is a real vector space. We have discussed number of examples in my earlier lecture. I will continue with few more examples to fix up the ideas. The example I take now is from the set of nth degree polynomials Pnx of the form Pnx is equal to a0 plus a1x plus a2x square plus an xn, where the x lies in given interval I and all the coefficients a0, a1, a2, an etc. are real. Then this set P forms a vector space with polynomial addition and scalar multiplication, which is defined in this manner. If I have two polynomials Pnx and Qnx, where the polynomial Pnx is a0 plus a1x plus an x raised to power n, and another polynomial Qnx of the form b0 plus b1x plus bn x raised to power n, then the addition of two polynomial is defined as a0 plus b0 plus a1 plus b1x and so on, and the last term is an plus bn x raised to power n. The idea is the coefficients are added, a0 b0, a1 b plus b1 is the coefficient of x, an plus bn is the coefficient of xn. Now this is called polynomial addition, while the scalar multiplication by a scalar c is defined as c Pnx is equal to c times the polynomial, and if you simplify it, it is c a0 plus c a1x plus c an xn. Now with these two operations, we say that this set forms a vector space. For proving this, first thing we have to do is we have to say that P is closed with respect to two operations, the addition and scalar multiplication. Now by this I mean to say that if I have a polynomial Pnx in P and a polynomial Qnx in P, then their sum is also a polynomial in P. So if you look at this definition, one can easily observe that when we add the two, the right hand side is also a polynomial of degree n with real coefficients a0 plus b0, a1 plus b1 etc. So this operation is closed with respect to, the set P is closed with respect to addition. Now as far as scalar multiplication is concerned, the same is true. Look at this, this c Pnx is also a polynomial of degree n. The only difference is all the coefficients are multiplied by c, but they still remain real. That is why this c Pnx is a polynomial of degree n, or we say that P is closed with respect to the two operations. The next property is that this addition is commutative as well as associative. Now this can be easily observed because Pnx plus Qnx, if this is so, then the coefficients of Qnx plus Pnx will be b0 a0, b1 plus a1, bn plus an and so on, and this simply means these are real coefficients, so they are commutative. So, Pnx plus Qnx will be the same as Qnx plus Pnx. Similarly, one can easily establish that this operation is associative. As far as the additive identity in the set is concerned, one can easily see that polynomial with 0 coefficients is the additive identity, and this belongs to the set of polynomials. Similarly, the additive inverse of Pnx is minus Pnx, and that means the additive inverse also exists in the set P. As far as the distributive properties they are concerned, they can also be easily checked because all the coefficients are real numbers and they satisfy distributive properties. So, these properties are satisfied. Then comes the existence of 1 such that 1 multiplied by Pnx is Pnx. So, the effect of this scalar multiplication with Pnx is that all the coefficients are multiplied by 1, and multiplying a real number by 1 will not change the coefficient, and that is why 1 times Pnx is Pnx, and this means that the set of polynomials P is a vector space. In the next example, we consider the set Q of all second degree polynomials of the form P2x is equal to a0 plus a1x plus a2x square such that the coefficients are related by the relation a1 is equal to a0 plus 1. So, it is not all polynomials, but only those polynomials which satisfy this relation. Then this set Q is not a vector space with respect to operation of polynomials of addition and scalar multiplication defined as P2x plus Q2x is equal to a0 plus a1x plus a2x square, this is P2x, plus b0 plus b1x plus b2x square is Q2x. It is defined as a0 plus b0 plus a1 plus b1x plus a2 plus b2x square, that is the coefficients are added together. The scalar multiplication C times P2x is defined as C a0 plus a1x plus a2x square, which is C a0 plus C1 C times a1x plus C a2 x square. Now, one may notice that this Q will not form a vector space as these two operations are not closed. By this I mean to say that if I add the two polynomials P2x and Q2x belonging to the set Q, then the resulting polynomial is a0 plus b0 plus a1 plus b1x plus a2 plus b2x square according to the definition which is given to us. A1 is equal to a0 plus 1 because P2x belongs to the set Q. Similarly, B1 is equal to B0 plus 1, Q2 belongs to Q, and from this one can see that A1 plus B1 is equal to A0 plus B0 plus 2. But if you apply this here, then this property requires this sum to be in the set Q requires that A1 plus B1 is equal to A0 plus B0 plus 1 instead of 2. So, this polynomial will not belong to the set Q, or we say this operation is not closed in Q. Similarly, Cp2x is equal to Ca0 plus a1x plus a2x square. If we take q2x to be 0, then Ca0 plus Ca1x plus Ca2x square, and this means Ca1 should be equal to Ca0 plus 1, but this is not true because A1 is equal to A0 plus 1 being P2x belonging to Q. So, this property is also not satisfied. So, this is also not closed in Q, and that makes Q not to be a vector space. Now, so far we were discussing real vector spaces. Now, we will be coming to complex vector spaces. The basic difference between the two is, in the real vector spaces, the scalars are taken from the set of real numbers, but in case of complex vector spaces, scalars are taken from set of complex numbers. So, we say that complex vector spaces are defined in the same way as real vector spaces, with the difference that scalars are permitted to be complex numbers. That means all the axioms need to be satisfied for this set of scalars. I will illustrate with this example. The set of n tuples V is equal to x1, x2, xn, where x1, x2, xn belongs to C, is a vector space in Cn with respect to vector addition, which is defined as x1, x2, xn belonging to V, y1, y2, yn belonging to V. The sum of the two is again an n tuple where they are components wise addition is taking place. So, this sum is equal to x1 plus y1 comma x2 plus y2, and the last is xn plus yn, while the scalar multiplication is defined as C star x1 x2 xn is equal to component wise multiplication Cx1 comma Cx2 Cxn, the last term. Now, you may notice that here I am considering all these numbers belonging to C. This is required to satisfy the closure property, because if these are not, if C is a complex number, then Cx1 will also be a complex number. So, if these x1, x2, xn are real, then the closure property will not be satisfied. So, this set forms a vector space in Cn. If you consider Rn real vector space, then there will be a problem. So, to satisfy the closure property, we consider set C, this coefficient, this x1, x2, xn belongs to C instead of R, and this means that the set V is nothing but Cn. So, Cn forms a vector space with respect to these operations. The additive identity can be checked easily, because the 0 vector theta is also in Cn, 0, 0, 0 is the theta vector, it is in Cn. So, this is a, rest of the properties can easily be checked. So, this forms a vector space. Now, in the next example, I am considering m by n matrices with complex entries instead of real entries. This example I have taken earlier, but at that time these are real entries, and we have seen that they form a vector space, and now we will see that with complex entries they also form a vector space with respect to matrix addition and scalar multiplication. The next example is the set P of all nth degree polynomial with complex coefficients. They form also vector space with respect to polynomial addition and multiplication by complex scalars. These are some easy straightforward examples, and one can easily work them out. Now, the next topic is subspaces. So, first the definition of subspaces. We say that let V be a real vector space with vector addition plus and scalar multiplication star, then a subset W of V is a subspace of the vector space if W itself is a real vector space with respect to the two operations plus and star. So, W itself is a vector space with respect to the two operations. Now, this is an example. If V be a vector space, then V is a subspace of V. We can say that V is a subset of V, and since V is a vector space, so this is a trivial example that V is a subspace of V. The another trivial example is the singleton 0 is a subspace of V, because this is additive identity. If it belongs to V, then it will be a subspace. These are two examples. Further, it is observed that addition is commutative as well as associative in W, because all the members in W, they belong to V. So, if it is associative and commutative in V, then it has to be in W. So, that is straightforward. The next thing is scalar multiplication. Again the same logic is applied, it is distributive in V, so it has to be distributive in W also, because W is a subset of V. The next thing is existence of 1 in R is also implied. So, if you have to prove that W is a subspace of a given vector space V, then we need to check the following 4 conditions. The first condition is that if alpha beta belongs to W, then the vector alpha plus beta must also belong to W. The idea is alpha beta belongs to W, but the sum alpha plus beta may be in V but may not be in W. So, one has to check that for each pair alpha and beta in W, its sum also belong to W, that is, this addition is closed in W. The closure property is satisfied. Second is additive identity exists in W such that alpha plus theta is equal to alpha for all alpha in W. So, if the additive identity must also be in W, without that it will not be a vector space. The next thing is that for each alpha belonging to W, there exists minus alpha in W such that alpha plus minus alpha is equal to the null vector theta. So, if alpha belongs to W, its inverse must also belong to W. So, this is also a requirement that is to be fulfilled by W to be a vector space. And the last property is that scalar multiplication is closed in W. For example, if C belongs to R and alpha belongs to W, then C star alpha must belong to W. So, the closure property with respect to scalar multiplication must be closed in W. So, if all these 4 properties are satisfied, rest of the properties are trivially satisfied because they are satisfied for V. So, this W will form a vector space. Now, one can notice that these 4 conditions can be translated into a single condition, like C alpha plus beta belongs to W for alpha beta belongs to W and C belonging to R. So, if this single condition is satisfied, then all these 4 conditions are implied. So, let us prove this. So, the first thing is a closure property. So, if I take C is equal to 1, because this property is satisfied for all C belonging to R, in particular if C is equal to 1, then alpha plus beta belongs to W for alpha beta belongs to W. So, if this property is satisfied for all C, then it will be satisfied for C is equal to 1, and this amounts to the closure property of vector addition in W. So, alpha plus beta belongs to W for all alpha beta belonging to W. So, if this property is satisfied, so this property is implied. Let us see the second property, additive identity. Here, if alpha is equal to beta and if C is equal to minus 1, if you consider this, then in this property, if you consider alpha is equal to beta, so beta minus beta is nothing but null vector. So, if C alpha plus beta belongs to W for all values of alpha, beta and C in R, then beta minus beta is equal to 0 will also belongs to W. So, this shows that there exists additive identity in W. So, existence of additive identity in W is established in terms of this condition. Then the next is additive inverse. We have given this condition. So, if I take C is equal to minus 1 and beta is equal to 0, the existence of beta is equal to 0 I have already established. So, if we take beta is equal to 0 and C is equal to minus 1, substitute it here, it is nothing but minus alpha belonging to W. So, if alpha is there, minus alpha is also in W, and that establishes the additive inverse in W. So, 3 properties have been established, and the fourth one is a closure property for scalar multiplication. So, to check this property with respect to this given general condition, then beta is equal to 0 if we substitute, then C alpha belongs to W. That means, for C in belonging to R and alpha belonging to W, C alpha is also in W, and that means closure property for scalar multiplication is also satisfied if this condition is satisfied. So, we can put a remark here that if W is a subspace of V, then C alpha plus beta is in W for each pair of alpha beta in W. And if this is there, then we can say that W is a subspace. So this is given in the form of the theorem. It states that a non-empty set W of V is a subspace of V if for each pair of alpha and beta in W and each scalar C in R, this linear combination C alpha plus beta is again in W. So if this condition is satisfied, then W is a subspace, or if W is a subspace, then C alpha plus beta is again in W. So we have proved this theorem. This property is also used as a definition for subspaces. So this is a very powerful property, and many times we use it as a definition for subspaces. Now I'll explain the definition with the help of an example. So example is taken from R cube. So if we consider V is equal to R cube and W is the set of all triplets where x1 and x2 belongs to R, but the third component is 0. Then W is a subspace with respect to usual operations. We know that R cube is a subspace with respect to usual addition and scalar multiplication. We have to establish that W is also a subspace in this. So to prove this, we consider C alpha plus beta. So I am using that very definition, that if alpha and beta belonging to W, then C alpha plus beta belongs to W, then it becomes a subspace. So let us consider C alpha plus beta. Alpha happens to be x1, x2, 0 belonging to the set W. Y1, Y2, 0 is nothing but beta in W. Then if you add the two, it is Cx1 comma Cx2 comma 0 plus Y1, Y2, 0, and finally we will have Cx1 plus Y1, Cx2 plus Y2 and 0. Now Cx1 plus Y1 belongs to R because x1 and y1 and C all they are real. So this also belongs to R. Cx2 plus y2 also belongs to R, and the third component is 0. So this vector belongs to W. So C alpha plus beta belongs to W for given alpha beta in W, and that means this W is a subspace. That's it. Now the next example, I consider again another subset of R cube. Here W1 is equal to x1, x2, 1, such that x1, x2 belongs to R. So instead of 0 now I am having 1 here, but one can see that W1 is not a subspace of R cube. So with respect to usual operations in R cube, so let us consider W1 as being given here. Now consider Cx1, x2 comma 1 plus y1 plus y2 comma 1. So we like to check whether C alpha plus beta also belongs to W1 or not. So we consider this left hand side, and the right hand side, according to the definition of the two operations, it becomes Cx1 plus y1, Cx1 plus y1, second component is Cx2 plus y2, and the third component is 1 plus 1 is equal to C plus 1. So this is not a subspace because we want here to be 1. Now this will be 1 only when C is equal to 0. For general value of C, this will not be 1, and that is why this right hand side will not belong to W1, or this operation is not, this scalar, this linear combination does not belong to W1, and we say that W1 is not a subspace. This is another example taken from the set of matrices. Let V is the set of all n by n matrices and W is the set of all n by n symmetric matrices. Then W is a subspace with respect to usual addition and multiplication. We have already seen that V is a vector space when V is the set of square matrices and we have the usual addition and multiplication operations. usual addition and scalar multiplication operations in V. So, it is a vector space, but we have to see that this set W of symmetric matrices, whether it is a subspace or not. So, let us start with V, which is set of n by n matrices, it is a vector space. Now, we consider set W, set of n by square matrices which are symmetric. We clearly know that W is a subset of V. This is the very first condition, W to be a subspace of V, that W should be a first subset of V. So, this we have established. Now, let us consider two members in W, alpha as Aij as square matrix, beta is Bij, another square matrix, such that Aij is equal to Aj. Why? Because they belong, these two matrices belong to W and they are symmetric matrices. So, Aij must be equal to Aj. Similarly, Bij is equal to Bji. Now, consider the linear combination Caij plus Bij. So, we consider typical element of this matrix Caij plus Bij. Now, this is equal to Aij becomes Aj. So, it is Caj plus Bji. So, we can say that a C alpha plus beta is also symmetric matrix. So, the operation is closed and W is a subspace. This is another example of taken from the set of matrices, but this time W is not a subspace. So, let us consider V to be 2 by 2 matrices and W is again set of all 2 by 2 matrices, but the condition is that this is non-singular matrices. So, we have a bigger set considering all square matrices of order 2, while W is only those square matrices of order 2 which are non-singular. Then W is not a subspace of V, where V is a vector space with respect to usual matrix addition and scalar multiplication. So, one can say that the null matrix is an additive identity of V. This belongs to V. It is a 2 by 2 matrix, it is a vector space. So, null matrix has to be there in V. But if we have null matrix also in W, then it is non-singular matrix. It is not a non-singular matrix. So, if null matrix does not belong to W, because null matrix has determinant 0, null matrix is a singular matrix. So, null matrix does not belong to W, but W has to be a vector space in its own right, then additive identity has to be there in W, and because of this reason W will not be a subspace of V. So, W is not a subspace of V. So, in the next example, we are again considering a triplet x1, x2, x3, they all belong to R with the condition that x1 is equal to x2. Then S is a subspace in RQ for usual operations. I have different types of sets, some forms subspace, some do not form subspaces. So, in this example, if this condition is satisfied, then they form a subspace. So, let us see the solution. Again consider the combination C alpha plus beta, which is equal to C x1, x2, x3, this triplet belonging to S, plus y1, y2, y3 belonging to S. Then simplifying right hand side, we will have Cx1 plus y1, comma Cx2 plus y2, comma Cx3 plus y3. Now, since x1, x2, x3 and y1, y2, y3 belongs to S, so they must satisfy the given constraint, that is x1 is equal to x2 and y1 is equal to y2. And using this condition, we can see that Cx1 plus y1 will also be the same as Cx2 plus y2. That means this constraint will be satisfied by this right hand side of C alpha plus beta, and therefore C alpha plus beta belongs to W, and hence it is a subspace. In the next example, W is equal to x1, x2, x3. but the constraint is now different. X1 is equal to 2x2 is equal to 3x3. We have to check whether it forms a subspace of R3 or not. The solution is on the same lines. We consider an alpha in W, which is a comma 2a comma 3a, because this condition has to be maintained, and beta is equal to b comma 2b comma 3b, be the two vectors in W. Then C alpha plus beta is C times the alpha vector plus the beta vector. Simplifying it, we will have C a plus b comma 2 times a plus b comma 3 times a plus b, and that means the condition x1 is equal to 2x2 is equal to 3x3 is also satisfied for C alpha plus beta, and that means C alpha plus beta also belongs to W, and this proves that W is a subspace. X2 square plus x3 square, and we will see that it is not a subspace. Now, the solution, in the solution we consider an example where alpha is 13 comma 2 comma 3 and beta is 25 comma 4 comma 3 are two vectors in W. One can easily see that they satisfy this constraint. 13 is equal to x2 square plus x3 square, 4 plus 9, and in this case 25 is equal to 4 square plus 3 square, that is 16 plus 9 is 25. So, these two satisfy this condition. But if you consider alpha plus beta, then the sum of these two vectors is 38 is equal to 38 comma 6 comma 9, but this vector does not belong to W. One can easily check that 38 is not equal to 6 square plus 9 square. That means if alpha and beta are these two vectors, then their sum alpha plus beta will not belong to W. Now, this is a usual way to show that a set is not a subspace. So, if you have to show that a set is a subspace, then you have to consider C alpha plus beta and try to show that C alpha plus beta also belongs to W. But if you have to show that it is not a subspace, then we will take some typical examples which show that C alpha plus beta is not belonging to W. So, this one simple example is enough to show that W is not a subspace. Now, this is slightly different example. Here I am considering the system of equations represented in the matrix form Ax is equal to theta. So, x is a column vector and theta is null vector. So, if I consider A as a square, A as a rectangular matrix of order m by n, and x is a column vector with n rows, then one can define the subset W as all the solution vectors which satisfies Ax is equal to theta. Then we have to prove that W is a subspace. So, we have A, the set of all rectangular matrices of order m by n with respect to usual operations of matrix addition and scalar multiplication. They form a subspace, they form a vector space, but as far as this W is concerned, W is a subset of A, but this will not be a subspace. To prove this, we consider x as x1, x2, xn a column vector such that Ax is equal to theta, y is equal to y1, y2, yn such that Ay is equal to theta. Now, we consider linear combination z is equal to Cx plus y, and we will see that Az, whether it belongs to this given set or not. So, we consider Az is equal to A times column vector Cx plus y, which is equal to C times Ax plus Ay. Since Ax is theta, so this is C theta is 0 and Ay is theta. So, C theta plus theta is also theta. So, Az is equal to theta. So, this z is also a solution vector. So, it forms a subspace. So, W is a subspace. In particular, the subspace W is called the null space of A. Now we define linear combination. A vector beta in V is said to be a linear combination of vectors alpha 1, alpha 2, alpha n in V, provided there exist scalars C1, C2, Cn in R such that beta is expressed as C1 alpha 1 plus C2 times alpha 2 plus C3 times alpha 3 and Cn alpha n. In short, we write it as summation I is equal to 1 to n Ci alpha I. It is a compressed form of representing this linear combination. Let us illustrate this with example. In this example, we have to show that the vector 1, 2, 3 is a linear combination of vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1. So, what we are supposed to do is, you have to express the given vector 1, 2, 3 in the as a linear combination of the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. That means, there exist scalars A, B and C such that 1, 2, 3 is equal to A times the first vector plus B times the second vector plus C times the third vector. So, if you add them up, then we will have A 0, 0 plus this is 0, B 0 plus 0, 0, C, and this gives me A, B, C. So, if there are two vectors, so if we equate the two vectors from left hand side and right hand side, they will be equal component wise, and that means A will be 1, B will be 2 and C will be 3. So, we can find, we have found A is equal to 1, B is equal to 2, C is equal to 3. If we substitute these values here, this will nothing but 1, 2, 3. In short, we have represented 1, 2, 3 as 1 times 1, 0, 0 plus 2 times 0, 1, 0 plus 3 times 0, 0, 1. So, we can say that 1, 2, 3 has been represented as linear combination of the given 3 vectors 1, 0, 0, 0, 1, 0 and 0, 0, 1. In the next example, again we are having vectors 5, minus 1, 1, and you have to express it as a linear combination of vectors 0, 1, minus 1, 1, 1, 0 and 1, 0, 2. The procedure is the same. We consider left hand side the given vector, right hand side the linear combination of the 3 given vectors 0, 1, minus 1, 1, 1, 0 and 1, 0, 2. This right hand side is simplified. It is C1 plus, the first component is C2 plus C3, the second component is C1 plus C2, no component is coming from this, then we will have minus 1 into C1, so it is minus C1 plus 2 times C3, no component is coming from the second vector. If you equate left hand side and right hand side component wise, then C2 plus C3 is equal to 5 and C1 plus the next is C1 plus C2 is equal to minus 1 and the last component is minus C1 plus twice C3 is 1. So, we have to solve these 3 equations to get the values of C1, C2 and C3. In the earlier example, the things were simple and we can straight away get the constants, but in this case we are getting 3 equations to solve them simultaneously. Now, to solve these 3 equations, one can observe that if you add these 2 equations, we will have first equations remain the same and the addition of these 2 equations give rise to C2 plus 2C3 is equal to 0, and that means we will have 2 equations in 2 unknowns C2 and C3. So, to simplify it, if I multiply this equation by 2 and subtract, so this and this will get cancelled and what we have is C2 is equal to 10. From this equation, this will get cancelled, C2 is equal to 10, and once you have C2 is equal to 10, you can substitute it here to get C3 is equal to minus 5, and once we get C2 and C3, one can get C1 from this equation, and that gives me 5 minus 1 1 as minus 11 times 0 1 minus 1, that is the value of C1, plus C2 which is 10 1 1 0, plus C3 minus 5 1 0 2. So, this vector 5 minus 1 1 is expressed as linear combination of these three given vectors. Now, the next definition is span of vectors. Let us say we have been given a set W of vectors alpha 1, alpha 2, alpha n with a set of vectors in a vector space V, then the set S of all linear combinations of alpha 1, alpha 2, alpha n is called the span of vectors alpha 1, alpha 2, alpha n. So, all the linear combination of this vector will form the set S, and that set will be called the span of vectors, and we denote the span of vectors as SW, that means the span generated from W. Now, since W is a subset of V and SW is linear combination of vectors of W, that means SW may be a subset of V, and since all the linear combinations are in SW, so SW is a subspace of V. Now, we are in a position to state a theorem which says that if W is a non-empty subset of vector space, then SW is the smallest subset of V containing W, is the smallest. It is not only the subset, but it is the subspace containing W. Now, to prove this, since every vector W in W is also in SW, because SW is a set of linear combinations of vectors of W. So, this W in W is also will be in SW, and that simply means that W will be a subset of SW. Now, we say that there be another, this no SW, let us say, is not a smaller subspace. Let us say there has to be another subspace T such that W is a subset of T. Now, we say that for such a subspace T, any linear combination of W is also in T, because it is a subspace. So, W is a subspace, W is a subset of SW, which is a subset of T, because all the linear combinations are in SW. So, they will be a subset of T, and that means that SW is the smallest subspace containing W. Now, the next definition is that set W is a spanning set of V if every vector in V can be written as a linear combination of vectors of alpha 1, alpha 2, alpha n of W. Now, it may happen that SW is equal to V, the span of W is V, then alpha 1, alpha 2, alpha n actually span V, or in other words, using this definition, one can say that W is equal to alpha 1, alpha 2, alpha n is a spanning set for the vector space V. Now, to determine whether a set W of vectors spans the given space V, then any arbitrary vector beta in V must be expressed as a linear combination of vectors of W. Now, this we illustrate with the example. The example is to show that the vectors 1 0 0, 0 1 0 and 1 1 1 spans R cube. So, let us consider any arbitrary vector A B C in R3, then it can be expressed as a linear combination of these three vectors C1 1 0 0 plus C2 0 1 0 plus C3 1 1 1. So, let us simplify it. This comes out to be C1 plus C3, the first component, the second component is C2 plus C3, and third component is simply C3. Equating right hand side and left hand side, we get C is equal to C3, the last component, and then from here B is equal to C2 plus C3, and here it is A is equal to C1 plus C3. So this C3 can easily be seen to be C, and once you get the value of C3 as C, C2 can be calculated as B minus C, and from this equation if you put the value of C3 as C, then C1 comes out to be A minus C. So for given values A, B, C, one can uniquely determine the scalars C1 as A minus C, C2 as B minus C, C3 as C. Thus we can say that these three vectors 1 0 0, 0 1 0 and 1 1 1 spans the vector space R3. However, in this example we have to show that the vectors 1 1 0 and 0 1 1 does not span the vector space R3. So let us see the solution. We consider an arbitrary vector ABC and consider it to be a linear combination of given vectors. So we write down ABC is equal to C1 times 1 1 0 plus C2 times 0 1 1. Simplify it. It is ABC is equal to C1 comma C1 plus C2 and finally C2, and this means A is equal to C1, B is equal to C1 plus C2 and C is equal to C2, and simplifying this we will get B is equal to A plus C. Now for the vector 2 1 3 belonging to R3 cannot be expressed as a linear combination of these three vectors, because if it has to satisfy, if it has to be represented as this combination, then it must satisfy this constraint. But if you substitute the value of B as 1, A as 2 and C as 3, then one can notice that 1 is not equal to 2 plus 3. That simply means that this vector 2 1 3 cannot be represented as a linear combination of these two vectors. So the vectors 1 1 0 and 0 1 1 fail to span R3. That is the conclusion. However, the span of these two vectors, that is 1 1 0 and 0 1 1, is the vector space V such that A comma A plus C comma C, where A and C belongs to R. So this is a vector space. So this is the span of this, but the vector which we have conserved will not fall in this vector space V. Now we have another theorem, and according to this, if we have two subspaces S1 and S2 of the vector space V, then the intersection of the two subspaces is non-empty and it is a subspace. Now to prove this, it is observed that the intersection of S1 and S2 is non-empty. Why? Because S1 is a subspace, S2 is a subspace, so theta has to belong to both S1 and S2. So theta must belong to S1 intersection S2, and that is why S1 intersection S2 is non-empty. Now we consider two cases. The first case is if S1 intersection S2 is a singleton theta. If that is the case, then it is a subspace of V, because this we have already established. But in the second case, if there are vectors other than theta in it, so let us say there are two vectors alpha and beta belonging to this intersection S1 intersection S2, then let us consider C alpha plus beta. That means we are trying to apply the basic definition of subspaces. So for alpha beta belonging to a set, if C alpha plus beta also belong to the set, then that set forms a subspace. That is what we are going to apply. So let us consider C alpha plus beta also belongs to S1 intersection S2. Now since S1 as S2 are subspaces, and that means S1 intersection S2 is also a subspace. C alpha plus beta belongs to S1, C alpha plus beta belongs to S2, so they belong to S1 intersection S2 also, and that means S1 intersection S2 is a subspace. That proves the theorem. However, if you consider the union of the two sets, it may not be a subspace. Now, to prove this, we have to establish by example. So, this is the example which we consider in example. S1 is equal to sets A comma 0, A belongs to R. So, it is a subset of R2. S2 is 0 comma B, B belongs to R. Now, we have to show that S1 union S2 is not a subspace. Now, the first thing is, in the solution we show that S1 and S2 are subspaces. One can easily see that A comma 0, A belongs to R, is a vector space. S2 is 0 comma B is also a vector space. So, S1 and S2 are subspaces of R2, because this is a subset of R2, this is also subset of R2. So, S1 and S2 are subspaces. Let us consider what is S1 union S2. S1 union S2 is all sets, all vectors which are either of the form A comma 0 or of the form 0 comma B, and AB belongs to R. So, that all these type of sets belongs to S1 union S2. Now, for this we consider alpha as 0 1 belonging to S1. Here I am taking B is equal to 1, beta is equal to 1 comma 0 belonging to S2, 1 is A. Now, alpha beta belongs to S1 union S2. Let us check this. C alpha plus beta is C 0 comma 1 plus 1 comma 0 is equal to, if you look at this, it is C 0 plus 1, it is 1, C plus 0 is 0, 1 comma C, where C is not 0. For C is equal to 0, things will be okay, but for C non-zero, this property may not be satisfied. So, if C is not 0, then 1 comma C does not belong to S1 union S2. So, S1 union S2 is not a subspace. So, while S1 intersection S2 will be subspaces for S1 S2 subspaces, but S1 union S2 need not be a subspace. Now, this result is generalized in the form of theorem 3, and what we say is that if S1, S2, Sn are subspaces of V, then the first result says that S1 intersection S2 intersection Sn is also a subspace, although we have proved for n is equal to 2. Similarly, S1 union S2 union Sn need not be a subspace, we have generalized it. The result we have proved for S1 union S2, but it can be further generalized to finite n subspaces. The result has been established for n is equal to 2. The viewers can prove these results, and the hint is they can use the mathematical induction to prove these results. Now, towards the end of this lecture, let me summarize what we have done today. I have started with review of the first lecture, in which I have given the definition of vector spaces, and then I have taken some examples. I have taken example of polynomials. Some of the polynomials, they form vector spaces. Some of the polynomials, when they are put under certain constraints, then they do not form vector spaces. I have discussed complex vector spaces. Then I have defined subspaces. After that, we have discussed linear combination, the span of vectors, and the next turn I will be discussing direct sum and independent and dependent vectors and bases. That is all. Thank you.